Hello, and welcome to Project Stepping Stones. The purpose of this project is to create a cost-effective renewable energy source on Michigan Tech campus powered by the people's footsteps. This system can allow the Houghton Hancock community to use stable, cleaner energy for public infrastructure. The inspiration for this project comes from a company called PavGen, based in the UK. They currently implement this technology in major cities. Our team distinguishes ourselves from PavGen in the generation type of the tiles. Where PavGen uses expensive synchronous generators in their tiles, Stepping Stones uses a cheaper voice coil to generate around the same amount of joules per step. Many different design considerations went into this project, including the calculations for potential output. First, the team needed to determine the most effective location. Working with the Urban Intelligence Lab, they provided the team with foot traffic data for high traffic areas around campus. The library has also provided extensive data for their building and the MUB entrances. This data helped provide a basis for the total energy output of the system if it were to be fully installed in the simulated sections. Using the foot traffic data, the team estimated the average energy generated individually and implemented on campus. On their own, each tile generates around 7 joules per step. Simulation has been a vital role within the team's modeling of the system. Using MATLAB Simulink to combine both the mechanical and electrical domain of the system has allowed the team to determine the power output of the system. This is done by modeling around Faraday's law, which takes into account the number of coils and the induced flux to determine the generated voltage. The process involved many trial and error in the components and overall prototypes. So far, the team has built a small-scale prototype using the voice coil and a rectifier circuit to light an LED. As for the development of the workable tile, the team has been researching the mechanical aspects for the stepping stone component of the tile, including rubber padding, springs, and more for the full-scale prototype. The prototype's power output will largely depend on the magnet strength and coil inductance. Once these are determined, the coil and load impedances will need to be matched to each other to ensure maximum power transfer. Because footsteps are largely intermittent, the generated energy may differ from day to day. Power electronics will be necessary to provide smooth DC output. Most importantly, the tile's vertical return mechanism must be durable, weather resistant, and safe for consistent use. The patent diagram on the right shows the hypothetical layering of the tile. Looking to the future, multiple goals have been set for the team. The primary goal is to keep refining the stepping stone for maximum power output and efficiency. One idea is to implement a piezoelectric component with the current voice coil system, similar to what Dr. Ruiz from University of Michigan presented in his latest research. This allows the mechanism and the tile itself to generate electricity. Once the stepping stone is complete, the design process for a large-scale walking path can be created. Thank you for your time in listening to the Stepping Stones team project.